Good morning, everybody. Last day before Thanksgiving break, or fall break, I don't know what it's called here. So we are going to spend today working on problems for the most part. And then I think, looking at our schedule, I think I'm going to do that for the most part the last week of classes as well. I think I'm going to try to generate problems that cut across the entire semester with different concepts we've had, and try to work on synthesizing how to work on complex problems. That's where I'm planning on going. So which question was it showing on your clicker? Was it showing just the first one?
Yeah.
Okay, sorry, I touched the iPad. So go ahead and click in your answer to this one. Which of these reaction coordinate diagrams shows an exothermic reaction? Has everybody got a chance to click in? Except for Mohammed? Everyone's got a chance to click in except for you, so you can join us. All right, we have 31. Does that sound about right? Looks a bit sparse today, so maybe that's about right. All right, so we have a large majority of the class answering one of these two.
Oh, wow.
Can I get Trey maybe to tell me which one you chose and why?
Y value shows the potential energy being higher on that than exothermic is the release of energy. So decreased potential energy is because the energy is being released.
Great. So exo means being released. That means that our products are lower energy than our reactants, and over the course, so this is reaction progress is what they label this axis, over the course of the reaction, you end up with something more stable and it releases energy. I agree. So then if we look at one of these, if we were to talk about the sign of delta H over the course of the reaction, which one of them would have a positive value for delta H? Go ahead and click in your answer. Once you've decided your answer, check with your neighbor, please. A couple more clicks, we're almost there. All right, and I almost want to close this out right now because we actually have 100% agreement, which is very rare in this class. Can I hear from, who can I hear from? Let's hear from Kyle. Which one of these do you think has a positive value of delta H and why?
So I chose A, like everyone else.
True.
Because the product's energy is higher than the reactant.
Okay, so what does that mean about the value of delta H? What does a positive delta H tell you?
So the change in H didn't go below the reactant amount of energy.
Okay, can I get someone else to add to it with your logic of how you think about that and how you describe what a positive and negative delta H is, Joey?
A negative delta H is exothermic, which means it releases energy. If it's a positive, then it didn't release energy, which means it's endothermic, so it's the other one.
Great. So I like that, comparing positive and negative delta H. Input of energy. Trey, did you want to add to that?
Well, just at the end of the reaction, you can see that the delta H is just higher, and that would indicate a positive value because it has more potential energy at the end of the reaction.
Okay, and I think what you're saying is related to delta H of the atomic combination. So if we look at what is delta H atomic combination of our reactants versus our products are going to be higher than our reactants. And I think if we're talking, so that's just static. What is our reactants? What are our products? The way that Joey was talking about it, I like as well, because it says, what is the overall change in energy of the system? In order to get our reactants to a higher energy product, we have to input energy. No matter what, we have to input energy, right? Both of them have this activation energy where we have to break some bonds. But in the end, we're still net overall a higher energy, which means that overall energy was input into that reaction. Great. I love that, the way you guys are describing that. I feel like we have a pretty solid grasp over endothermic, exothermic in these diagrams. So let's see if we kind of look at another question, which I think I had on the worksheets in the last couple of days. We're talking about the burning of octane. Which of these two paths releases more energy? Pick your answer first and then check with your neighbor, please. And we should have an option C up there, I apologize. All right, check with your neighbor once you've decided your answer. All right, we have a split class. So can I get someone to describe your group's thought process, Gail?
Question. I don't know if it matters. Do you mean like release as in like production of energy or actually going into the outside? Like
Going into?
Like, because like the car they'll produce the same amount of energy, but one of them is releasing it into the outside, and the other one is using it for something else, like transferring the wheels, the parts of the engine.
Okay, great. So I like that you're thinking about energy can be transferred either as heat to the surroundings or by doing work, right? Those are what you're talking about. Does this state how it's releasing the energy?
No.
No. This is just talking about the release of energy. So you said both of them would be the same. Why? So you picked answer C.
Because, well, the burning of octane is the same amount of energy.
Yeah, regardless of how it's being released, whether it's being released as heat, a combination of heat and work, or just as work, which doesn't exist. But if that could, both of those two pathways, you can see going back to the way a couple people are describing this, the potential energy of the reactants versus the products is identical, regardless of the path that we use to get there. So one of them you can put in a drum and just burn it. Remember we talked about a car idling? It's almost the same thing, except the car idling did have some very lightweight parts moving, so there was a little bit of work done. In this case, we can say that there's almost zero work. Okay, there's some gas molecules that are being pushed out of the way, so maybe there's a tiny, tiny bit of work being done. Over here, we're saying that there's work being done, the car is moving, and the car is inefficient, so it releases a lot of that energy as heat. So what I want you thinking about is that potential energy diagram does not exist outside and separate from this. There's just two different ways of looking at the same information. So basically here, we're looking at the same type of graph. Actually, if we go back to this, which one of these two diagrams represents the burning of the gasoline in a drum? Which one of these two diagrams represents the gasoline? In that left example, we're burning it in an open fire. Is it endo or exothermic?
Well, it's exo, because otherwise you wouldn't have, because otherwise burning in a drum would release heat.
So it's exothermic releasing heat, right? Which one of those two diagrams represents driving the car and burning it? The change in energy of that system.
Same one.
Same one, but maybe delta H wouldn't represent the entire change. Maybe it'd be enthalpy change, which is more looking at heat, and then also there'd be work as a component of that. But the initial energy of our reactants and products doesn't change regardless of what path we use to get there. Questions? Josh? Maybe this is not the most accurate diagram for pathway B where we do work as well, because this is assuming it's really in the form, energy transferred in the form of heat. All right, so my goal for you guys today, we're going to spend a little bit of time since we do have the screen up and running. You guys are welcome to come grab a seat if you'd like, or? Oh. So we're going to spend some time looking at the molecules that we didn't have a chance to do last class because our projector went down. Can everyone look around their seats and see if you see a set of keys? Is there anything on them? A lanyard? Any keys? Any lanyard? Moab, do you find it? No.
I don't know what color it is.
All right, and then we're going to spend a bit of time, good luck, we're going to spend a bit of time thinking about how to calculate the change in enthalpy of a reaction from atomic combination, but also from individual bond energies. And then the last part of class is we're going to determine how much distance you can travel, thinking about a combustion reaction and how much fuel we have, how much energy is transferred, all those kinds of things. So we're bringing that all together. So last class, I mentioned verbally, and you guys had it on your piece of paper, that biofuels typically start from having a triglyceride that comes from seed of some sort. And these molecules then undergo some sort of chemical transformation to be more usable. One of the properties of larger molecules is that they have higher boiling points and they're more viscous. What does viscous mean? Thickness. Great. So this is a very thick molecule. Think about syrup, right? Think about olive oil, those kinds of things. They're relatively thick compared to water. And then think about gasoline. Gasoline is pretty non-viscous, right? It evaporates pretty easily. And if you're thinking about using it in a combustion engine, if you're piping it through gasoline lines, you don't want something that's like honey or oil, right? It's much more difficult to transport. You also have to spray it into a mist inside the engine in order for it to combust. So this molecule, while it has a lot of potential to release energy when you break these bonds and form new ones, it would be much more helpful if it was smaller chunks. And so what we do in order to take this triglyceride and make it into a biofuel is we break it apart. So the first question that I have, and we're going to do a target, is I want you to look at this molecule and determine what part of the molecule, you can only select one, that's kind of what Clicker allows you to do, has the lowest electron density, and maybe relating that to the terminology you guys have been comfortable with before. Where is a partially positive part of this molecule? You have the structure on the back side of your worksheet as well at the bottom, if you want to take a look at it in person. But go ahead and touch the screen on the part where you think has the most partially positive component of this molecule. And then go ahead and talk to your neighbor about where you chose and why.
There's a bit of a problem. You can't select the entire area.
You can only put one dot. So you can pinch and zoom the screen if you want to zoom in a little bit. So what is this relating back to? We're talking about partial positive parts of the molecule. Can I get a hand raised? How are we orienting ourselves to look at a molecule like this and think of partially positive parts of the molecule? Matt?
It's electronegativity.
That's part of it. Can you explain a little bit more?
Electron density.
Okay. How does that relate to electronegativity?
It's when more electrons are attracted to one atom than another.
Okay, that's huge, okay? One of the first things I hear when students talk about what part of a molecule attracts water, right? That was on the last exam. And I've been going through the exam wrappers. It takes me a long time because there's a lot of text. So I haven't finished them yet. I will try to finish those on Monday. A lot of students say oxygen is electronegative, and so it attracts the positive, partially positive part of water. Why is that statement incomplete or wrong, really? Love?
They all are electronegative. They have it's like a variety of electronegativity. So oxygen is more electronegative than hydrogen.
It's then something else, right? If a bond is going to be polar, it has to be the thing that Matt just ended up saying after he said it's about electronegativity, and he said, well, if you compare two atoms and one is more electronegative than the other, it pulls the electrons more towards the electronegative atom. Oxygen by itself is not polar. It's not pulling electrons from anything. So if you have O2, right, you have two oxygens bonded together, that is a nonpolar molecule. But if you have oxygen bonded to a carbon, or oxygen bonded to a hydrogen, oxygen is more electronegative than something else. So that relative electronegativity value makes it a polar bond, which makes the oxygen partially negative because it pulls a little more electron density towards itself. If it's pulling more density towards itself, it means that the other bonding partner has less electron density than it started with, which means it's a little bit positive. So if we're doing that, if we're looking at this molecule, what are we looking for? Matt, do you want to continue on that?
An electronegative bond greater than 1.5 or greater difference.
Okay, so I would say a bond, maybe reword that a little bit. So I'd say that a bond with two atoms that have greater than a 0.5 difference in electronegativity. And so what atoms bonded together do and don't have that? So if we look around the molecule, we have carbon, 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 carbon. Each one of these carbons has 4 bonds, so there's multiple hydrogens. Is a carbon-hydrogen bond polar? No. We consider that nonpolar, even though there's a little difference in electronegativity. Carbon-carbon, is that polar? No. Nope. Here's a carbon-carbon double bond, so each one of these only has 1 hydrogen. All nonpolar, right? Nonpolar, nonpolar, nonpolar. We get over here at this end of the molecule, and if we take a look at where people selected, it's a little bit hard to see, but we have the majority of our clicks over on the left side of the molecule, so that's great. And then the question is, which of the two sites is going to be more electropositive? And you can say the same for any of the 3 components of it. Is it going to be the one on the far left, or the carbon double bonded oxygen connected to an oxygen? This is called an ester, and this is called, I guess that's, I don't know, there's a name for that. It's part of the ester, but it's the outside part of the ester. Which one of those two? Talk to your neighbor. Which one of those 2 sites is going to be more partially positive? All right, can I have a volunteer to describe what your group discussed? Amber, can I hear from you? Not sure which one of the 2? Why? Why the one with 2 oxygens instead of 1 oxygen? Okay. Lenny? Okay, so you're describing if it's going to attract water or not, which is definitely an outcome of what we're talking about. So if we're looking at this part of the molecule versus this part, it's useful to draw in all the dipoles of the polar bonds. And so oxygen is more electronegative than carbon. We can draw the electrons being pulled towards oxygen, and that's true for all 3 of those bonds, right? This carbon has a hydrogen, and a carbon bonded to it. All those are nonpolar. So this one has electrons being pulled away by 1 atom. This carbon has a carbon, oxygen, oxygen, so it has electrons being pulled away by 2 different oxygens. That means that out of those 2 sites, the one that's going to be significantly more electronegative, or electropositive, sorry, partially positive, is going to be the one with electrons being pulled away by 2 different atoms. So that is the reactive site. So we're talking about organic chemistry now. Next semester, or next year, sorry if you guys take organic chemistry, it is all about identifying areas of high electron density and low electron density. So anytime you see a carbon double bonded to an oxygen, you're going to automatically think low electron density, especially if it's attached to another oxygen. So in organic chemistry, this carbonyl functionality, the C double bond to O, is almost always going to be the site of reactivity, You'll get into some more complex reactions, but if you can identify that and say because electrons are being pulled in two different directions, that's where something is going to interact. And so what is going to interact in this case is you would add sodium methoxide. Maybe it's easier to write it as CH3. You're going to add an aqueous solution of sodium methoxide. What's that going to separate into when you put it in water? So it's going to be aqueous, which means, do you see any ionic bonds in there that are going to separate when you put it in water?
Sodium and the methoxide part.
So going back to looking at differences in electronegativity that we were talking about, sodium and oxygen have a very large difference. They're always going to be considered ionic. And so when we put that in water, we're going to end up with sodium plus, aqueous, and methoxide, it's called. So this is like hydroxide, but it's a carbon connected instead of an oxygen. Now we have a negative charge. What part of the molecule is that going to be attracted to? Where did we just identify was the most positive part of the molecule? So we are going to... So we have 3 lone pairs of electrons around the oxygen. Those are going to be attracted to the most positive part of this molecule. So here's another way to draw it. So this time I'm looking at the bottom one instead of it. All 3 of those are relatively electropositive sites.
So in that sense, would the single bonded oxygen be the most electronegative part of the...
So both of these oxygens are relatively electronegative,
But that one has two carbons attached to it.
but this one has 4 electrons that it's pulling towards itself as well. So I don't know, you could say one over the other is more electronegative. But carbon can never have 5 bonds. So when these lone pair, one of the lone pairs attacks this carbon, that carbon will have 5 bonds. We can't have that. So that means that one of the bonds has to break, and the one that breaks is typically the double bond, pushes electrons up onto that top oxygen, and now that top oxygen, it had 2 lone pairs, it has 3. So we have this intermediate where the OMe, Me stands for methyl, CH3, is attached to that carbon. But that's not very stable. That carbon is now super electropositive, right? Because it has 3 different oxygens pulling off. And so those electrons, that lone pair, will come back down and break a bond in that molecule. Yeah, Angel?
Why does the double bond break?
So the double bond pushes up because that's the most flexible site. And if we do that at first, we end up with a negative charge on an oxygen instead of a bond breaking. I think both of them happen is probably a better explanation. But one of the possible, the ways that in organic chemistry, the way we describe a mechanism is one of the reasons why this is such an electropositive site is because it can push electrons up here and still be somewhat stable. But then those electrons push down, and they can either break the methoxide back off, that's totally possible, and some of the time it'll break off this carbon-oxygen bond. That happens 50-50. If the methoxide breaks back off, the same thing's going to happen again, and there's a 50-50 chance of breaking those 2 oxygen-carbon bonds again. When it does finally break the left one, we end up with a fatty acid methyl ester, known as methyl oleate. That's what we were doing calculations for last week. And then we end up with this guy. How many times can that happen for this molecule? It can happen once for each of those. And then if we have some methanol around or methoxide, we end up generating more methoxide. This reaction happens over and over again. So it's a catalytic cycle. You only need a tiny bit of methoxide or sodium methoxide, and then you just have to have some methanol around. This regenerates OMe minus, and then that goes on and does another attack, breaks the molecule apart. So in the end, We have glycerine, which is this part of the molecule. These are all OHs. And we have 3 methyl oleates. That's a little preview of next year.
Thank you so much.
All right, so now we're talking about these fatty acid methyl esters that were made by using sodium methoxide and or triglyceride. We did some calculations on this last week, right? So last week being Wednesday, we figured out, based on a table of standard enthalpy of atomic combination for each of these molecules, we figured out the methyl oleate we figured out how much energy required to break all the bonds in the reactants. We could add up standard enthalpy of atomic combination for each of those. We could do the same thing for the products. Remember, we spent some time talking about the stoichiometric coefficients were really important, because for every of the 27 moles of oxygen we break apart for every methyl oleate, it requires an input of 498 kilojoules to break apart that O double bond to O. So we have to have that happen 27 times. So we said this is an exothermic reaction. The total change in enthalpy of this reaction was the difference between the enthalpy of the reactants and products, or you could say it's an input of this amount of energy, a release of this amount of energy. And by doing that, we found that that total change in energy was 9,181 kilojoules for every mole, or 9.181 megajoules. A mega is 1,000 kilo. Sound familiar? That was our summary. It was kind of quick at the end of last class. I wanted to go back and revisit it. So the next question I'm going to ask is, can we do these calculations any other way? If we didn't have that table of enthalpy of atomic combination, what other information could we use, and how would we calculate the total change in enthalpy of this reaction?
You can calculate it by the bond energy.
So what do you mean by the bond energy?
That's all I know.
Okay, so I gave you guys a table there. If you're thinking about these molecules breaking apart, are any of these atoms still bonded to each other in the products? Every single one of them breaks apart, rearranges into something else. Same with all the O2s. So with that table you guys have, could you calculate how many carbon-carbon bonds are broken, how many carbon-hydrogen bonds are broken, how many carbon-oxygen single bonds, carbon-oxygen double bonds are broken? You have the structure, right? See what I'm getting at? Could you calculate how many carbon-oxygen single and double bonds are formed in the products? How many oxygen-hydrogen bonds are formed in the products? You know the energy for each one of those. Do you guys want to do that? Go ahead and take 30 minutes again.
Wait, at what time do you use 0 for O2 gas for delta H, and at what time do you use the 490?
So it's a very relevant question. So the question is, when do we use 0 as oxygen is a single atom gas, or O2? Whatever you do, stick with the values in one table. So on the exam, even if I gave you 2 different tables of values, you would have to stick with one for every calculation, because they might have a different 0 point, like you're saying. It might be O2 as a 0 point, it might be O as a 0 point. If you stick within one set, the relative values are all going to match up and line up. So, do you guys think that we're going to get the same change in enthalpy if we thought about individual bonds breaking and forming as if we did the standard enthalpy of atomic combination values? So we have, not sure why my computer's frozen. So we could go through, right, and say, in the reactants, how many of each of these do we have? Anyone take a guess? How many CHs do we have?
17.
Okay. So we could go through and count individually. how many of each bond type we're breaking. Is it a positive or a negative delta H for each one of those? We're breaking bonds.
Are we doing the big molecule?
We're saying our reactants. This is a picture of it. That's the formula of it. Breaking bonds requires energy, so it's what sign for delta H? Plus. All right? And we could go ahead and calculate that out. Does this look fairly close to what we had before?
No.
For bond breaking, it's negative side. All right, and then we could do the same thing. So we can compare it to that. We could do the same thing then for the products. So in 19 moles of CO2 and 18 moles of H2O, how many carbon-oxygen double bonds do we have? How many carbon-oxygen double bonds are in 19 CO2 moles? How many COs are in each CO2?
It's before Thanksgiving break, I'm sorry. Wait,
Have you guys seen this molecule before?
Yeah.
Okay, so how many CO double bonds are there for every CO2?
32.
And then we have 19 moles of them, so that means we're going to have, our math skills are strong. And then we have 18 water molecules, each has 2 OH bonds, right? So you get the idea of how we could figure out the amount of energy. And then is this going to be a positive or negative delta H?
Negative.
These are all going to end up being negative, right? Because we're forming bonds, we're releasing energy. So if we go back and kind of look at it this way, we're basically saying that we had to input a sum of all the bonds is this much energy. We're forming all these bonds. It's the sum of this much energy being released. And we can find the difference between those. Hess's law, have we even used that word yet?
No.
So Hess's law basically says that to find the change in enthalpy of a system, you can add up the individual parts. That's all it is. You have a decent amount of questions, maybe 3 or 4 questions in the homework that are about Hess's law, looking at different reactions. If we sum up reactions, we can look at the sum of all the reactions is the sum of the enthalpies. There's a tutorial that walks you through it. And there's a CHEM tour I sent out in the announcement yesterday, I believe, that also walks you through how to set them up, and it shows you with the tutorial. So in this case, the total change in enthalpy is still the identical number. It's not always going to be identical. All right. What I did here was the way I found the enthalpy of this molecule was by adding those values up. So they're almost identical ways of doing it. But the difference is going to be that a lot of times if you use the values of individual bonds, that's the average bond energy for a CO bond. And the average might be different from molecule to molecule based on what's around it. You will need to do both of these approaches in order to find the change in enthalpy of a reaction on the ACS final exam. So there's some practice problems I think I have in the homework, but conceptually, hopefully this is pretty straightforward. If not, there's plenty of time in office hours next week. All right, so let's go ahead and do a question.
Thank God it's multiple choice. We got a 25% chance.
20%? 5 answers?
Oh! Well.
All right, quicker question. How much energy is released if we burn enough methyl oleate to produce 3,709 gallons of water? Here's the delta H that we calculated for the reaction. Is there any additional information you guys might like to have?
The answer?
The answer? I will not give you the answer. If you let me know what other values you need, I might provide them to you.
Maybe the molar ratio?
You guys know the balanced equation, right?
Sure.
This is combustion of methyl oleate. That's what we've been talking about. That's what we just did the calculations on. So hopefully you know the... All right, so moles to gallons would be great, maybe something smaller. So on the back page, you have some conversions. Gallons to liters, you have the density of water. So you should be able to use these in order to answer this question. So go ahead, take a few minutes, make sure your answer is in the correct units and the correct sig figs, please. And raise your hand if you get stuck and would like some guidance. Does everyone have the balance equation written down? 1 methyl oleate was at 27 oxygens to 19 CO2s and 18 waters. And I would advise you to think unit conversions here. I see some people doing lots of small calculations. Try to think about writing it out as one giant conversion.
Oh, yeah, and then 27?
Not NG,
Oh, megajoules for every mole of methyl oleate.
You gotta love it. I know it looks easy to throw that.
Do not know this is right.
We don't even need the manual since it's per volume. I could just sub in the budget page for this one.
We can't do that. H2 up, right? And then what's this diagram? Do those cancel out? Maggie, those don't cancel out.
Yeah.
Go back to your
That's the game. Oh, okay.
But that's not right.
Well, so those just don't cancel, right? You can't cancel grand
Online, it's
and then you.
3.785.
Yeah, I was gonna say the water.
It's 2 hours late.
Does that make sense?
Kinda.
Yeah.
Just fine.
Calculate it out.
Okay. That's grams of water, and then 18 moles. H2O is 1 mole.
Oh, so we don't have to put negative, since it said these already.
That is true.
So that energy is per mole of energy.
No, it's just it's just 9.1. You know what he does? It's like the open mouth. Yeah. Why are you doing it like this? This way confuses me. Okay. Okay, so that's grams. Okay, so you're converting to grams, moles, grams of water, moles of water, moles of MO, and then you converted it to grams.
Turn it back into this.
Oh, you went. Okay.
I was designed and I can pull it back.
Okay. And then you went. Okay, so that's per.
Caleb, do you have a question?
No, actually, well, from the water.
What is this right here? So this is how many moles of, tell me what these moles are of.
It's a lot of joules. That's a lot of water, though.
You're saying for every 18 moles of oil, there's 1 mole. Okay. All right. Looks like a good setup. All right. So let's talk through this. I think most people got started and found a starting point for their calculation. So what's our starting value for a calculation?
Well, I started by turning the amount of water to liters of water.
Okay, so your starting quantity, and this is what I saw people doing a lot of little calculations. I want you to go back and think about it as dimensional analysis. So our starting quantity is going to be 3,709 gallons of water. I saw a lot of people using G. Why is G not a great? So grams, gallons, if it's in the same calculation, don't use the same abbreviation for it.
If you do big G, is it gallons, right?
Big G is giga.
Oh.
So I just did GAL. All right? And then, Gail, you said you converted from gallons to, so 1 gallon is 3.84 liters. Why is that useful?
Because for liters we can get the mass of the grams.
Okay, so there's one more step we might want to do. It depends if you're comfortable with milli or not. Then we're going to do 1 liter is 1,000 milliliters to use the density, which is
1.010 grams. And then
I saw a lot of people just making that 1. So make sure that if you have a density, that will make an impact. The bigger a number is, the more that's going to impact it. So please be accurate and use the values that we have. So then what do we do? Now we know exactly how many grams were in this amount of gallons of water that we produced. So what do we do next?
we turn from grams to moles of H2O.
So 18.02 grams of H2O is 1 mole of H2O. Here comes the tricky part. There's 2 ways of doing this. How did you do it, Gil?
I did the ratio, so 18 moles of H2O equals 1 mole of MO. And then I had the moles. MO, and then multiply that by the 9.181. And then get the result.
Great. So this blue number right here, the way that you interpreted that is for every 1 mole of methyl oleate, this is how many megajoules are released. How is the other way? What's the other way we can use this? Aaron. Great. And I would add one additional part there for every 18 moles of water produced. So just adding produced to that. We know that this is the number of moles released. That statement holds true for everything in that balanced stoichiometric equation that we wrote. For every 19 moles of CO2 produced, this is how many megajoules of energy are released. So what could we do differently? Where could we modify this to make it a little bit shorter? So we could basically combine these last 2 steps. Did you notice that 1 mole of methyl oleate kind of cancels out if instead of that you said for every 18 moles of water you release 9.181 megajoules of energy. Savannah.
Why is it that you use the reaction value instead of like the enthalpy value specifically for methyl oxide?
Because the amount of energy released in a reaction does not depend on the product alone. It's like saying, how high or what's our change in height? I am at sea level. That doesn't really tell you much, right? So we have to say, where did we start and where did we end? So it's extremely important that we don't use these values. We use these to calculate the total change, and then we use the total change per whatever the stoichiometric ratio is in the equation to find that out. So this question states released, so our final answer would not need to have a negative sign. If I said, what is delta H of that combustion, you would need to put a negative sign there. I would be very careful about what you do there. Before everyone packs up and leaves, this is pulling together so much that we've done this semester. The question on the back side of this page is the same thing, but taking it 1 step further. Try it. Work on it. Come to class prepared on Monday after Thanksgiving. Having tried to work through this, I think if you guys can do what we just did, you just need to think about 1 or 2 additional conversion factors here in order to get to that. And then think about efficiency. Maybe efficiency is important. All right, I hope you guys have a great break. Make sure to complete your homework. Let's crowdsource the correct answer.
The next one, yeah.
So we have a whole bunch of different units. So how many sig figs should our answer have? Our answer should have 4 sig figs because everything else are conversion factors we can look at more accurate versions of. We should not use those to limit our answer. Those should be 4 sig figs. And then, does that help, Gail? Looking at the answers? It looks like there's a lot of people that basically said this, but this would be 4 sig figs. So 4.074 times 10 to the 5th megajoules. Does that sound right?
What percentage of our final grade, like, is the final exam